Welcome to my problem solving class on my Advanced Microeconomics. Problem set 1 on the first problem number 1. And this problem is about checking properties of preference relations. Now consider the following preference relations of two goods, good x1, good x, and y. And here is the conditional preference relation. We need to find upper contour set, lower contour set, and indifferent set of bundle 2, 1 and interpret them. And then we are going to check whether these preference relations are rational, monotone, and convex. So let's start the solution. First, we build intuition behind this preference relation. So preference relation says that individual prefers x to y if first component of bundle x, that means x1, contains at least one unit less than the first component of bundle y, that means y1. So here the condition is x1 should be greater than or equal to y1 minus 1. The second condition is the second component of bundle x contains at best one unit more than second component of bundle y, and the second component for second component x2 should be less than or equal to y2 plus 1. These are conditions for this preference relation. So let's move on. We are going to find upper contour set, lower contour set, and indifferent set UCS, LCS, and IND of a given bundle 2, 1. First, upper contour set. So if we apply the conditions on first component, we get first and second component, we get x1 is greater than or equal to 2 minus 1, and x2 is less than or equal to 1 plus 1. That means our upper contour set is x1 greater than or equal to 1 and x2 less than or equal to 2. This can be presented in figure 1.1. The upper contour set is the for all bundles to the area bounded by x2 equal to 2 and x1 equal to 1. That means the area below the deep dashed line, horizontal deep dashed line, and to the right of vertical blue dashed line. Similarly, we can find the lower contour set as x is less than 3, less than or equal to 3, and x2 is greater than or equal to 0. By applying the condition that x2, x1 is greater than or equal to y1 plus minus 1, and x2 is less than or equal to y2 plus 1. So we find this, and this is also represented by the by figure 1.1. Those bundles to the above x2 equal to 0 and to the left of x1 equal to 3. Now let's find the indifference set. And indifference set, we know that indifference set is the intersection of upper contour set and lower contour set. That means IND equal to upper contour set intersection lower contour set. And we see that upper contour set is x1 is greater than or equal to 1, and lower contour set x1 is less than or equal to 3. So we can find a range for x1 for indifferent set is x1 less than or equal to 3 but greater than or equal to 1. Similarly, we can find the range for x2 by using this range, x2, this range. x2 is less than or equal to 2, but greater than or equal to 0. All right. So we can see it graphically, which is the rectangle in the bottom center of figure 1.1. So this is common area between upper contour set and lower contour set. I can figure out by putting A, B, C, D. This rectangle is our indifference set. All right. So let's check completeness of this preference relation. So graphically, it is easy to locate that completeness doesn't satisfy here. So we can find an area like this area. Any point on this area which is not covered, which is not included in upper contour set, lower contour set, and indifference set. So if we see that x1 is greater than 3, strictly greater than 3, or x2 is strictly greater than 2, this area, our preference relation does not specify whether they belong to upper contour set, lower contour set, or indifferent set of bundle 2-1. So this range, this area is incomparable with 2-1. So we can say that the preference relation is not complete here. This can be proved in other way by using the counter example. So let's use counter example, and we know that the definition of completeness is if x is weakly preferred to y, either x is, the definition of completeness is either x is weakly preferred to y, or y is weakly preferred to x, or both. So this is the condition for completeness. But the counter argument is neither. If neither x is weakly preferred to y, nor y is weakly preferred to x, we can say that this preference relation is not complete. Let's take two bundles, x for x 1, 2, and y 4, 6. So if we apply the condition for the preference relation, we see that take the first component, 1 and 4. So let's see. The condition is x1 should be greater than or equal to y1 minus 1. So if we see that 1 should be greater than or equal to 4 minus 1, that means 4 minus 1 means 3. So 1 should be greater than or equal to 3, which is not possible, which is not correct. So we can say that x is not weakly preferred to y. However, for the second component, it is said that 2 should be less than or equal to 6 plus 1. So it is all right, but for the first component, we can say that this is true. Okay. Similarly, we can say that y is not weakly preferred to x if we take the second component. So x2 means here x2 means y2 should be less than or equal to x2 plus 1. So if we see that y2 is 6 and should be less than or equal to x2 is 2 plus 1, that means 6 should be less than or equal to 3, which is again not possible. So that's why we can say that y is not equal, so y is not weakly preferred to x. So in these 2 points, we say that there is a counterexample for completeness, and so we can say that neither x is weakly preferred to y, nor y is weakly preferred to x, which implies that this preference relation is not complete. So let's now see the transitivity. And we know that for transitivity, if we have 3 bundles x, y, z, then if x is preferred to y and y is preferred to z, then x should be preferred to z by transitivity. Okay. We can also use here the counterexample to see whether the transitivity property holds or not. So these are the 3 bundles. So let's take one by one. So if we take the example of x versus y, then what happens? For the first condition, x1 should be greater than or equal to y1 minus 1. So take this. 2 should be greater than or equal to 3 minus 1. That means 2 should be greater than or equal to 2. It's all right, no problem. For the second component, x2 should be less than or equal to y2 plus 1. So let's see, x2 is 1 and should be less than or equal to 4 plus 1. So 1 should be less than or equal to 5. It is also satisfied. So we can say that x is preferred to y. Let's see whether, let's see the preference relation between y and z, y and z. So here we apply the same rule and same condition and find that for the first component, 3 should be greater than 4 minus 1. So 3 should be greater than 3 or equal to 3. So it's all right for the first component. For the second component, 4 should be less than or equal to 6 plus 1. That means 4 should be less than or equal to 5. which is also all right. So we can see that this is also true. Y is weakly preferred to Z. What about the final between X, whether with, if we find that X is weakly preferred to Z, then we can say that transitivity is all right. So let's see whether this is all right. So similarly, we can find that for X1 and Z1, so X1 equal to 2, it should be less than or equal to 4 minus 1, here 4 minus 1. So 2 should be less than or equal to 3, which is not correct. So preference relation doesn't, so we can say that this is not the case. So we can say that this preference relation doesn't satisfy transitivity. Our next task is to find the monotonicity. So what about the monotonicity? Monotonicity is, but if we increase the first component or second component by a unit, suppose first component by epsilon and second component by delta. If we increase first component by epsilon and then see whether it is monotonicity is applied, or if we apply delta, add delta and see monotonicity is applied or not. And the condition for epsilon is, it is positive. Delta is also positive, but very small amount. So let's check. So our bundle is now, if we take the first component, increment of the first component, our bundle is now X1 plus epsilon and X2, and we compare it between X1 and X2. So if we compare them, so then we can say that X1, the first component is greater than or equal to first component of the second bundle, X1. So X1 minus 1. So if we simplify that, that is epsilon is greater than minus 1, which is all right, no problem, because we know that epsilon is positive. So epsilon should be greater than minus 1. For the second component is X2, and we compare it for X2 from the second bundle. So X2 should be less than or equal to X2 plus 1. So X2 cancel out. Sure. So we can say that 0 should be less than or equal to 1, which is also all right, no problem. So we can, if we increase, if we increase the amount of good one by epsilon, we see that monotonicity is applied. Similarly, we can check for good 2 by increasing good 2, that means X2 by delta, positive delta. We can find the same or similar result. Similar argument can be applied for single good X2. Let's take both increment of both good. So suppose we increase, now our comparison bundle is X1 plus epsilon and X2 plus delta for first bundle, and we can see whether this is preferred to X1, X2. If we can see that this is true, then monotonicity is applied. So for the first component, we can see that x1 plus epsilon should be greater than or equal to x1 minus 1. So x1 cancel out. So epsilon should be greater than or equal to minus 1. So it is all right, no problem, because we know that epsilon should be positive. For the second component, x1 plus delta should be less than or equal to x2 plus 1. So if we cancel out x2 and x2, so we can find that delta should be less than or equal to 1, which is which doesn't necessarily true for all times. So we can say that there is a condition for the monotonicity to hold is that delta should be less than or equal to 1. If delta is greater than 1, then monotonicity doesn't apply. So this is our this is our condition. So in order, our preference relation is monotonic, but one condition is there: delta should be less than or equal to 1. So if delta is more than 1, then this preference relation is not monotonic. Okay. So let's see an example. So we say that alpha and epsilon is positive and delta is also positive, but condition is delta should be less than or equal to 1. So let's take epsilon equals delta equals 2. Then our bundle is x1 plus 2 and x2 plus 2, and we compare this bundle with x1, x2. So for the first bundle, x2, here we see that x2 should be greater than or equal to x1 minus 1. So x1 cancel out. So 2 is greater than or equal to minus 1, which is obvious, no problem. But what about the second component? Second component is x2 plus 2 should be less than or equal to x2 plus 1. So x1, x2, x2 cancel out. So we can say that 2 should be less than or equal to 1, which is not possible. That's why we have seen that our condition was delta should be less than or equal to 1. So if we say that delta is equal to 2, then our condition doesn't apply here. So monotonicity is doesn't hold if delta, the increment of the second bundle, second component of the bundle is increased by more than 1. Okay. Now let's take the last property, convexity. And we know that convexity implies that the upper contour set must be convex. So this is very important. So upper contour set must be convex. And for upper contour set must be convex, if x1 and x2 is weakly preferred to y1 and y2, then convex combination of these two bundles is also weakly preferred to y1 and y2. This is the condition for convexity. So symbolically, you can write this. Convex combination of these two bundles weakly preferred to the, bundle y1, y2. we can simply write in this way: lambda x plus 1 minus lambda y should be weakly preferred to y. So this is convex combination of x and y. If it is weakly preferred to y, then we can say that these two bundles are convex. That means upper contour set is convex. So if we apply the condition for first component and second component, we can see that the first, so our comparison is now lambda x1 plus 1 minus lambda y1 is first component, and second component is lambda x2 plus 1 minus lambda y2, second component, and which should be, first component should be greater than or equal to y1 minus 1, and it is less than or equal to y2 plus 1. So this is our condition now for convex combination of two bundles and the bundle y1, y2. Okay, so if we simplify this, we can see that lambda x1 minus y1 should be greater than or equal to minus 1 for the first component, and lambda x2 minus y2 should be less than or equal to 1 for the second component. So if this is true, which is similar to the original bundle condition for the bundle x1, x2, for x1, x2 weakly preferred to y1, y2. So condition was x1 should be greater than or equal to y1 minus 1, and x2 should be less than or equal to y2 minus 1. And this could be said x1 minus y1 should be greater than or equal to minus 1. And this implies x2 minus y2 should be less than or equal to 1. And this is similar to that for convex combination. Convex combination of x and y. This is also true, and this is satisfied. The conditionality is satisfied here. Why? Because we know that lambda is 0, 1. So we can say that convexity is applied. Our final property of the reference relation, convexity, is satisfied here. So this ends our problem set 1.1. Let's move on problem set 1.2. So this problem is about convex preference, and the problem reads: consider a concave utility function ux for for denoting consumption bundle of with n component. In addition, consider the transformation of the utility function into another utility function, fx. Vx equals function of the original utility function, which is strictly increasing and concave. We have to show that preference represented by Vx, that means transformed utility function, must be convex. We need to show this. So let's start digging 1.2. To show convexity in preference, we need to show that, suppose there are three bundles, x1, x2, and y. So if x1 is preferred to y, x2 is also preferred to y, then convexity says that the linear combination of x1 and x2, that means x bar, also satisfy this condition. That means x bar is preferred, weakly preferred to y. And if we apply this rule to utility function representing the preference relation, this property implies that utility from x is greater than or equal to utility from y. Utility from x1 is greater than or equal to utility from y, and utility from x2 should be greater than or equal to utility from y. If this is the case, then their linear combination, that means convex combination, also satisfy this property. The linear utility from the linear combination of x1 and x2, that means x bar, should be greater than or equal to utility from the good y. So this is all about convexity. So if we apply this rule on transformed utility function Vx, then what happens? So Vx bar, since the transformed utility function is concave, our problem says that it is concave function. So if it is concave, then it must satisfy that the Vx bar is greater than, this is the condition for property for concave function. So if this is greater than, Vx bar is greater than or equal to alpha Vx1 plus 1 minus alpha Vx2, then Vx is a concave function. What does it mean actually? The meaning of this equation is the linear combination of the utility from bundle x1 and x2. This is linear combination of utility from bundle x1 and x2. If it is lower than the utility from the linear combination of bundle x1 and x2. So Vx1, x2 is Vx1, x2, Vx bar is actually linear combination. Is, suppose our lambda is lambda x1 plus lambda 1 minus lambda x2. So this is Vx bar, and we can it will be clear if we see figure 1.2. You see here in figure 1.2, this is a ux. I mean, this point is convex combination of the original utility. That means if we say that ux bar is lambda x1, lambda u x1 plus 1 minus lambda u x2. And this point is vx1 and this point is vx2. So this point is, suppose it is a lambda. So here in the picture it is used alpha. So we can also it's no problem. We can use lambda also. So lambda v x1 plus 1 minus lambda v x2. So this is the point, and this point should be less. If this point is less than this point is vx bar. So if it is ux bar, then this is function of x bar. That means vx bar, because we know that this is our transformed utility function, which is vx is function of ux. So this is vx bar. And this vx bar is, if this is greater than this, then our utility function is concave. So in this graph depicts that Vx is concave. Now we are going to see that the concave function is convex. So using the definition of transformation, we can rewrite the inequality, the above inequality. That means inequality in the last slide. If we use the transformation, I mean, in terms of the function, we can write this. So here, we convert this as a function. So we know that Vx is a function of Ux. So we just convert all these Vx into function of Ux, okay? And here we see that these are utility of x1 and x2. Okay, so we know that utility function of utility of x is strictly increasing. Then we can say that strictly increasing over bundle y. So we can say that this is greater than or equal to function of utility from y. If we say that x is x1 and x2, so we use both good, which is greater than or equal to y. Then we can write the above inequality again into this, like this. So function of ux bar is greater than or equal to alpha function of ux1 and 1 minus alpha function of ux2, which is in terms of u, which is greater than or equal to this one. function ux bar is greater than or equal to function uy. From this two inequality, we can simplify this, and finally we can use the property of transformation that is strictly increasing. So function of ux bar is greater than or equal to function of uy, implying that, and this implies that ux is greater than or equal to uy. I mean, utility from x bar is greater than or equal to utility from y, and this shows this is what we are looking for. Our question was show that the preference relation presented by Vx must be convex. So by using the convexity, so if this is true, then Vx is convex. So this ends our problem number 1.2. Let's move on to problem 1.3 is about WARP and rationality. So we are given a choice rule C dot defined over budget set universal B, and assume that it satisfies revealed preference, weak axiom of revealed preference, WARP. So question is, does this choice structure guarantee a rational preference? So let's start our solution. Let's prove it by using an example of a choice rule C that satisfies WARP, but it doesn't satisfy the transitivity. So let us consider consumption set with three goods, X, Y, Z, and the following budget set. Budget set contains XY, YZ, XZ. So let's now consider the choice rule among this budget set. So this choice rule is, the first choice rule is X is preferred over Y. Second is Y is preferred over Z. And third choice rule is X is preferred, Z is preferred over X. So notice that this choice rules satisfy WARP. However, such a choice rule implies X is chosen over Y, then we can say that X is strictly preferred to Y. If Y is chosen over Z, then we can say that Y is chosen over, Y is strictly preferred to Z. But we say that this preference relation is rational. It must satisfy the property of transitivity as a consequence. Then we must have this lineup: X preferred to Y, Y preferred to Z, Y preferred to Z, and then X must be preferred to Z. But X preferred to Z contradicts the choice rule. We have seen in the choice rule by CXZ, that means Z is chosen over X, whereby the decision maker only selects Z when both X and Z are available to them. So the choice rule entails Z is strictly preferred to X, implying that the choice rule, despite satisfying WARP, doesn't guarantee the rational preference relation. So transitivity is violated. So if transitivity is violated, then we don't need to see for completeness. We know that for the property of rationality contains two properties. That means combination of two properties are called rationality. One is called completeness, another is transitivity. Any violation of any of the axioms or properties, we can say that rationality properties is violated. So here, although the choice rule, given choice rule satisfies WARP, but it doesn't guarantee that this choice rule is this preference relation is rational. So this ends our 1.3, problem 1.3. So let's move on to problem 1.4. So this is interesting problem. Problem 1.4 is about lexicographic. So the question is, very simple question. Does the lexicographic preference relation induce a choice structure that satisfies the weak axiom of revealed preference, WARP? So let's move on the solution. As we see in the hint, we can prove this statement. That means we can prove 1.4 in two steps. First is we need to show that every lexicographic preference relation, every lexicographic preference relation is rational. And second step, we need to prove every rational preference relation satisfies WARP. So in this step one, we define lexicographic preference relation. So X is weakly preferred to Y if and only if the first component is greater than the first component of X is greater than first component of Y, or if the first component is equal to the first component of Y, then the second component is greater than or equal to second component of X2 is greater than or equal to second component of Y2. This is the definition of lexicographic preference relation. To show that this preference relation satisfies rationality, we need to show that it is both complete and transitive. So completeness, in the first problem 1.1, we define the completeness. So what is the completeness? Either X is preferred to Y, or let me write either X is preferred to Y, or Y is weakly preferred to X, or both. If this is true, then X and the preference relation is complete. So in order to prove this, we need to show that X is not preferred to Y. If we can prove this, then we can prove that this is true. That means if we can disprove that X is not weakly preferred to Y, this implies that Y is weakly preferred to X. If we can prove this, that we are done with completeness. So let's see. So X is not weakly preferred to Y can be expressed as if first component is greater than or equal to first component of Y is greater than or equal to first component of X, and if the first component of Y is not equal to first component of X, or second component of Y2 is greater than or equal to second component of X2. Remember, in our definition of lexicographic preference, we used or here and here. Now for the not preference, I mean X is not preferred to Y, we use or and if. Or if and logic. So we can say that expression 2 describes Y contains weakly more of good one, than X does, implying that lexicographic preference relation weakly prefers Y over X. That means our condition for not weakly preferred implies Y is weakly preferred to X. And this is what we have we wish for. So if we prove that, we can say that this is the case. And by definition, we say that this is also true. And by counter logic, we say that this is also true. So we have seen that either or. So any of these property, if these are true, then completeness holds. Now let's go for transitivity. And for transitivity, let's take another bundle, because we know that for transitivity, X preferred to Y, Y preferred to the third bundle Z, and transitivity implies that X is preferred to Z. Okay, so let's take X, Y, Z and apply the definition of lexicographic preference relation. We now have a couple of or if and logic with the preference relation. And if we combine them, we can find the 4 possible cases in which X preferred to Y and Y preferred to Z. What are the cases? Case number 1. This case is this one and this one. Combination of the first condition of both preference. Case 2. Combination of the second condition. Case 3. Combination of the first and second. Case 4. Combination of the second and first. So we need to check for transitivity in all 4 possible cases in which X preferred to Y, Y preferred to Z. In case 1, in case A, case 1, X is greater than 1, X1 is greater than Y1, Y1 is greater than Z1, Y1 is greater than Z1, and obviously this greater than or equal operator says that X is preferred over Z. In case 2, X1 equal to Y1 and X2 is greater than or equal to Y2, and Y1 is equal to Z1, Y2 is greater than or equal to Z2. So from these two, combination of these two implies X1 is equal to Z1 and X2 is greater than or equal to Z2. If we read these two conditions, combined condition, we figure out that X1 equals Z1, X2 is more than or equal to Z2. So, and in addition, we see that X1 equals Z1, X2 is. So this implies that X is preferred to Z. So here also transitivity validates. In first case, transitivity holds. Second case, transitivity validates. Let's see the third case. Third case says X1 is greater than Y1 and Y1 equals Z1, Y2 is greater than or equal to Z2, then obviously X1 is greater than Z1, which implies again X is preferred over Z. Transitivity also holds here. Let's see the D, case D or case 4. So case 4 is combination of X1 equals Y1, X2 is greater than Y2, and Y1 is greater than Z1, then X1 is greater than Z1, which obviously implies X1, X2 is preferred over Z1, Z2. Again, we see that transitivity holds. So in conclusion, we say that under which x is preferred over y is preferred over z may arise in all four cases that x is preferred over z, confirming that this preference relation is transitive. We check all four cases under which x is preferred over y is preferred over z. In all four cases, we obtained x is preferred over z. That confirms that preference relation is transitive. Therefore, we have seen completeness and transitivity properties are satisfied by this preference relation. So we conclude that lexicographic preference relation is rational. In the second step, we need to prove that every rational preference relation satisfies WARP. So in order to do that, we recall the choice relation that satisfies WARP. So if for some B in universal B, X and Y is member, X and Y belongs to B, that means budget set, we have the choice rule X belongs to CB, that means our choice rule is X belongs to C dot, that means CB. Again, for any alternative bundle included in universal budget set with XY belong to B prime, where Y belongs to CB prime, we must have X belongs to CB prime. This is the definition of WARP in terms of choice rule. Okay. Then if X is revealed preferred to all other bundles in B. So suppose our budget set, we take budget set B in universal B. Let us assume that XY belongs to B and the bundle X is revealed preferred to all other bundles B, then by the property of revealed preference, X is C star B in all other bundles. And this implies that X is preferred to Y. So if X is revealed preferred, so X must be in C star, that means optimal choice on bundle B with preference relation. This implies X is preferred to Y. we can use a symbol here R. That means X is revealed preferred to Y. So to check whether WARP is satisfied, suppose that for other budget set B prime, it is explained above here, in universal B, that also contains bundle X and Y. We have that bundle Y, if bundle Y is revealed preferred, so by the definition of revealed preference, we can say that Y belongs to C optimal choice rule, which implies that Y is revealed preferred to X. Sorry. Revealed preferred to any other bundle, suppose Z, which is also Z is inside Z belongs to beta B prime. And since we have also seen that X is revealed preferred to Y, that means by transitivity, because transitivity, we have already proved that this preference relation, that means lexicographic preference relation, is transitive. Because the preference relation is rational, we obtain that X is preferred to Y and Y is preferred to Z by the second bundle beta prime, B prime. Then we can say that X is preferred to Z. That means transitive. So for all Z in B prime, this implies that X belongs to optimal choice rule of budget B prime and preference relation. Therefore, we can say that WRP is satisfied. So in first step, we have seen that lexicographic preference relation satisfies rationality. That means complete and transitive. This preference relation is complete and transitive. And in the second step, we have seen that every rational preference satisfies WARP. This ends our problem number 1.4. Let's move to problem number 1.5. And this is our last problem in this chapter, preferences and choice. Preferences and choice are the first chapter of our course, chapter number 1. 1.5 is about checking properties of Cobb-Douglas utility function. So let's consider the Cobb-Douglas utility function of this type. And you see that the number of root is n. And we are given to show that this utility function satisfies additivity, homogeneity of degree k, and homotheticity. So we need to prove these three properties of Cobb-Douglas utility function. So let's move to a solution. In this solution, we can degeneralize the Cobb-Douglas utility function above for two goods for the sake of simplicity. So this is ux is x1 to the power alpha 1 and x2 times x2 to the power alpha 2, where both x1 and alpha 1, sorry, this is actually alpha 1, alpha 2 is positive. Both are positive. Now, what is the definition of additivity? For a utility function to be additive, we need to obtain the for a utility function to be additive, the marginal utility of good x or good k, marginal utility of good k must be independent. That means first derivative of the marginal utility of good k with respect to any other good should be equal to 0. This is the definition of additivity. If this is not equal to 0, if this is not equal to 0, then we can say that it is not additive. So first take the marginal utility of good k from this utility function. So this is the marginal utility of good k, which is ak over xk times this function, the original function. This utility function is not additive since marginal utility of additional amount of good k, that means marginal utility of good k depends on the amount of other goods. So if we take the first derivative of marginal utility with respect to another good j is not equal to 0. Okay, so this is our this is the remainder of the marginal utility of good k with respect to. So if we take the first derivative of this good, and because this is the multiplication sign, and we cannot avoid any x j, whether it is x2, 3, 4, whatever, any xj, we cannot, if we take the first derivative of this, that means del, that means this one, del k del xj, del uk del xj, which could be, so which is not equal to 0. That is what our point. So for simplifying this, so because it is a complex equation, so let's simplify this with two goods. So here our simplified Cobb-Douglas utility function. So it will be easy to locate whether additivity is satisfied or not. So here the marginal utility of good 1 is this one. That means if we take the first derivative d, sorry, let me see whether we can, so d u1x by d2, so this will be equal to what? So here this one is dx, this one is x2, so we can find that this one is alpha 1 divided by x1 times x1 alpha 1. So this is obviously not equal to 0. So we can see that marginal utility of good K with respect to another good is not equal to 0. That's why we cannot, that's why the utility function is not additive. Sorry, this is not the right one. So this could be alpha 2 x2 alpha 2 minus 1. So this is a function of both x1 and x2. Okay. Similar argument can be applied for good x2. Now let's check for homogeneity. Oh, we know that for homogeneity we need to increase both input and output. That means right hand side, left hand side by a common factor. Let's take theta, and this is our original utility function. So let's multiply by theta both sides. And if we see that the original function is multiplied by that factor with some degree, then we can say that this function is homogeneous with homogeneous of degree of that degree. Okay. So here we see that this function is homogeneous of degree sum of sum I equals 1 to n alpha I. So this is the power of theta. So here this is the power of theta. Homogeneous of degree and sum of AI. So if I equal n equals 2, then the utility function is homogeneous of degree alpha 1 plus alpha 2. So when alpha 1 is, we know that when alpha 1 plus alpha 2, that means degree is more than 1, a common increase in theta means that all goods produces a more than proportional increase in the consumer's utility function. These are the properties of homogeneous function. So if we multiply input by a common factor and the output is increased by that factor or more than that factor or less than that factor, depending on the degree of homogeneity. So if it is the degree of homogeneity is more than 1, it is called increasing. Less than 1 means decreasing, and equal to 1 means constant. So if alpha plus 1 is less than 1, alpha 1 plus alpha 2 is less than 1, a common increase theta in the amount of all goods produces a more than less than proportional increase in the consumer's utility level. So if it is equal to 1, then generates a proportional increase in the utility level of the individual. That means his utility increased exactly by theta. For more than 1 means more than proportional increment. Less than 1 means less than proportional increment. Now, let's move to homotheticity. So homotheticity means that when our utility function satisfies homotheticity, our utility function satisfies homotheticity since it is homogeneous. So first condition for homothetic function is the original function must be homogeneous. Okay, so we can apply the monotonic transformation. So monotonic transformation of homogeneous generates homothetic function. So our original function is ux. If we apply monotonic transformation of this ux, suppose vx, which is function of ux. So then this function is homothetic function. Homothetic because the original function is homogeneous. Because ux is homogeneous, then the monotonic transformation of this ux is homothetic. Okay. Now, there is a simple way to check homotheticity in practice. We have to find the marginal rate of substitution, MRS, of any two goods, suppose good K and good L. So MRS KL. So if the MRS KL, so this is our function for n equal to 2. And this is our transformed function. So we use the logarithmic monotonic transformation. So we can find the marginal rate of substitution MRS from this monotonic transformed function. This is our MRS. So simple way to find the homotheticity of that function is that MRS between the two goods is just a function of the consumption between the two goods. That means function of, good X1 and X2. If MRS is function of these two goods, which is not which is independent of the absolute amount consumed. To clarify, let's move forward. So here is our reminder for MRS. MRS between good L and K. K is not equal to L. Only depends on the ratio. So if it is only depends on the ratio of these two goods, but independent of any other good. So if the MRS between L and K is only the ratio of these two goods, not the independent of any other good, suppose XH. So you don't see a XH here. That means MRS, so MRS between LK should be equal to 0. No, not this case. MRS, the first derivative of MRS, del MRS between L and K with respect to any other good, suppose XH, should be equal to 0. That means independent of other good, other than the goods inside the MRS. That means any third party, third good. And this implies that because MRS is the slope of the indifference curve, then MRS depends only the proportion of good L and K, not any other third good. Graphically, this implies that the slope of the indifference curve coincides along any ray from the origin. So here you see that the ray from the origin, the slope of the indifference curve. So if we go for monotonic transformation, so the ray, the slope remains the same. That's why the slope is parallel through any ray from the origin. Here, good X and AX. So for the upper IC, that means for upper U2 and lower U2, the ratio, it increases by the same ratio, X divided by Y. This MRS remains the same for homothetic function. And this is because the original function is homogeneous. So if homogeneous, then the monotonic transformation, whether it is linear or log linear or natural linear, the ratio between the two goods are same. That means MRS is just function. So if we see the remainder of this MRS, so we can say that this is just function of the good to the ratio of two goods. So simply we can check the homotheticity by using MRS. So if MRS is the only function of these two goods, then the function is homothetic function. If it is dependent on any other goods, then it is not homothetic. So this ends our problem 1.5 and also ends our problem set 1. Thanks for watching.